Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Xin Xie, the Chief Engineer and R&D Director at Orbbec. Xin earned his doctorate in mechanical engineering and has published a scientific research book, 23 journal papers, and 14 conference papers with more than 1,200 citations. Today he's discussing a quantitative evaluation method for depth accuracy and precision metrics. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Xin, we appreciate you for taking the time to present at the 4th Annual Vision Spectra Conference.
Okay, good morning, everyone. This is Xin Xie. I'm the Chief Engineer from Orbbec. So today is my great pleasure to have the chance to talk here today. The topic today I want to share with you is quantitative evaluation method for depth accuracy and precision metrics in depth cameras. To start with, so today there's an increasing needs and the use of depth cameras in a lot of different industries. So this slide actually showing you some customer examples that they use Orbbec cameras for their productions and commercializations. So for most of those customers, when they first work with us and first they get in contact with us, the first and the most frequently asked question to us is, hey, Orbbec, you have a lot of depth camera there available, like stereo cameras, time-of-flight cameras, and structured light cameras. And how do I make sure I pick the right one for my application? And how do I make sure my camera is giving me the reasonable right readings, right? Okay, so to answer those questions, usually the customer start with camera picking based on specs from the datasheet first, but most importantly is after that, they will take some camera samples and do the actual data testing on the camera itself. So if we call it pick the right camera is the first step to the success of the commercial, then the first step to that success to guide you to that success will be find the right way to test your camera. Then that testing data will tell you, okay, which one you should pick. When we talk about camera testing, so different customers, different users may do that differently. However, in general, there's only two approaches that you could take. So you take either the subjective evaluation on the camera or you take the objective evaluation on the cameras. Sometimes people also call that quantitative testing or qualitative testing on the left and quantitative testing on the right side. Okay, so for the customers, they use the depth information or the point cloud information to just determine, say, okay, if the object is there or not, should my robot avoid it or not? To answer such kind of yes or no question, usually the customer only need to take a qualitative testing on that. So which is not the focus point here. So you can see a lot of things like the OpenCV testing there. You can refer to those. Today, our focusing will be on the right side, which is how to test the camera quantitatively. So usually this is the needs from the customers that really care about the numbers and the readings from the depth camera. And they use the camera for like 3D reconstruction, scanning, LAM applications, because for those applications, the final reconstruction accuracy, the modeling accuracy, and the measurement accuracy is purely based on what a camera can provide you in depth. Okay, so that's why they need to test that carefully and have those solid data, charts, and histogram to support their decisions. Okay, so currently on the market, okay, if you see all the depth cameras, that category by technology they use mainly only three mainstreams. Okay, the structured light depth camera, the stereo vision depth camera, and the time-of-flight depth camera. So here on this slide, those three equations on the top, which are the governing equation for each of those technology, which explains how each technology measures the distance. So for example, the structured light one, it measures disparity D here, which is the disparity between the camera image and the pre-recorded calibration image. Once you measure that disparity, you use that to calculate what's your distance. We also call that depth. And stereo vision one also makes use of the disparity. However, that's the disparity between the left and the right camera. And then you use that to calculate what's your distance and depth. So different from the other two, time of flight actually measures the phase change. You can also understand that as the time it takes for a laser to shoot out and come back. Okay, then use that information, you calculate what's the depth and the distance for time of flight cameras. So then if you take the first derivative to those governing equations, okay, so that becomes the arrow functions. So if you observe all those arrow functions for each technique, what you find here is the structured light and stereo vision cameras, the depth arrow, okay, will naturally grow with the distance by power of 2, while the TOF camera, actually the arrow grows linearly with the distance. So that naturally gives the benefits and advances of TOF technology beyond the other two. Here is a prediction from the math side, from the equation side. Later, I will have some real tested data, then you can see how everything looks like in there. So today, what I'm going to do is I will introduce you a detailed testing workflow, testing procedure, and we will use that testing flow and the procedure with the same post-processing method to process the data we capture from 3 example cameras here, which covered in 3 main technologies. The Femtomega is the representer for the I-12 camera, the Gemini 335 is the representer for the stereo vision camera, and the Astra 2 is the representer for the structured light cameras. So we get the data from the same capturing procedure, and we post-process the data using the same method. Then from the data side-by-side comparison, then you start to directly see, okay, what's the strength for each technology, what's the limitation for each technology. Okay, so then let's first jump into the first part of the presentation, the depth accuracy metrics. So let's start with the setup first. So on the right side here, you can see the testing the setup pretty simple. The target is a white flat wall that everybody can find. Okay, then you will set up an optical ray in front of that, make sure it's perpendicular to the wall. And then you can move your camera and laser distancers on this optical ray to capture data at different locations. And then you need a fixture to fix your laser distance meter and your test camera together. Okay, make sure they move rigid together. And then you use the laser distance meter reading as a ground truth, and you use the test camera depth reading value as input. Then you can start to calculate what's your accuracy, what's your precision, and other metrics. Okay, so first of all, after you set your setup up, and you need to make sure everything's aligned, the camera and the laser distancer is perpendicular to the wall. After that, you start to connect your data. And in this example, what we did is we record data from a broad range from 0.5 meter to 6 meter. And we take one data at interval of 100 millimeter each. Okay. And then at each camera, like a recording position, we record one depth image. And here, make sure you turn off all of those post-processing filters. Okay, so make sure you only use the raw data to do the comparison, which is fair for all the cameras and also straightforward for you to understand. Okay, once you connect all those data ranging from 0.5 meter to 6 meter at the interval of 100 millimeters, then you need to select your region of interest, which we call that ROI here. So here we picked 3 different ROI. One is 9% of the full frame, which indicated as a green block here. And the second ROI we pick is 20% of the full frame, which is the red block here. And the third ROI we pick here is 81%, which is a yellow block here. Okay, there are 2 reasons we need to pick multiple ROIs to study this camera. The first reason for that is we want to take the same metrics measured from different region of the frame so that we can compare the data and figure out, okay, is there any lens distortion issue happening on camera? And if my pattern is dark and bright, dark, bright here, and does that have any impact on my final evaluation and the final accuracy of the depths? So those are the topics that go why we need multiple regions. The second reason we need different region is, imagine you have a limited wall, say 3 meter by 3 meter, and if you pick a very large FFA and with large ROI here, you easily get the ceiling to be captured or the floor to be captured or some other stuff to be captured within that ROI at very close distance. then in that case, you won't be able to get some data at long distance. So in order to get some more data at longer distance, you have to shrink your ROI down a little bit so you can avoid the ceiling, the floor, and other stuff in the environment. Okay. So after you select your ROI, and we need to do a little bit of very minimum pre-processing, which is we need to count how many pixels are valid within the ROI. And then you remove those pixels without any reading there. Okay, with that also you can help you to calculate what's the fill rate within there, which is using the number of the invalid pixel divided by the total number of the pixels, then you know how much percentage of the pixels are not valid, then you know your fill rate. Then after you remove those invalid points, we start to calculate what our metrics. So first thing is the accuracy. You just simply take your depth reading from each pixel and subtract that to the minus to the ground truth value. Then you get what's your absolute error here. And in this case, you could get some positive value or negative value. Positive means your depth reading is bigger than the ground truth, and the negative means the depth reading is smaller than that. Okay. So second metrics we measure here, which is the root mean square error. Okay, we'll call that RMSE, which is the most widely used measure to present error. So here what you do is you fill in your measure data as Y, and you subtract to the Y cap, which is the ground truth value you get from your laser distance reading. You take the square and you sum it, and you take a mean and you take a root on it. By doing that process, actually you removed all the influence from the positive or negatives, and it's all positive here, and it's easier to understand and be presented and understood. The third one we take the measurement here is the standard deviation, also short for STD. That's the most common way you judge the data to see how stable the data is, how concentrated the data is. So by only looking at those numbers, it's not very easy to understand. So that's why in this workflow, we try our best to present the data in a visualized way, okay, in a chart or whole map or histogram. So here then, if you look at this data on the chart, is more straightforward, okay. So what's showing on this chart is the RMSE value with distance. So basically the vertical axis is the RMSE error you calculated within your ROI. And you see there are three kinds of data plotting together on here. The red data points are the actual measured data from the 81% ROI, which is the red block here, okay? And because the region is too big and about 2 meters in my setup, I start to see the ceiling and the floor. That's why I stopped here, okay? And for the blue box, which is 25% ROI, I'm able to measure up to about 3 meters, a little bit more than 3.5 meters, then before I see the ceiling and the floor. And the purple one here, which is the longest line here, which is 9% of the ROI, is the most center part, and that can enable me to measure up to like 6 meters in this example. So if you compare the data of those red dots, those blue dots and the purple dots, you see them overlapped very well. And that means this testing camera have no issue with the distortion, right? The distortion everywhere is corrected by the algorithm, and there's no influence on the final result by the lens distortion. Second thing you can observe here is you see, even though the speckle pattern here you see on the IR image, somewhere is brighter, somewhere is darker, but you see the result, there's no significant impact from there. Otherwise, you will see this purple line will be way off from the other two lines, right? But it doesn't happen. That means the algorithm handles the distribution of the pattern very well, instead of it tracking the intensity for that, okay? So that's the comparison between the three sets of data that give you some feeling, say, okay, is the camera distortion well taken care? Is the speckle pattern well taken care here? The other aspect on this is your measured, how good your measured data is aligned with your theoretical prediction. Okay, from here, as we mentioned in the previous slides, from the equation observation, what we found is the error grows as power of 2 with distance, right? So you should get a second power polynomial from the theoretical error, which we calculated this green line from the equation we provided above and using the camera specs here, okay? And then you locate your testing data on here, you see all those data align very well on this chart for the second power polynomial, which means your camera is working as expected. On the right side, it's the same data, but a different representation, which is use the data on the left side, divide that by the distance z, then you get an error percentage from here. And if you take a second power polynomial, divide by z, then you get the first order polynomial, right? Which means that's a straight line. And you also see the predicted straight line and the actual data aligns very well. So that gives you the confidence, okay, the camera is to give you the right thing and the right accuracy. And the last thing you want to check is, okay, does this camera falls into the specs, the accuracy specs that the manufacturer provides you, right? So for this camera, specifically Gemini 335, the spec on the box we marked on there is like 2% within 2 meters. So at 2 meters, you see actual test data tell you it's below 1 meter. It's far below the marked specs, which is means this camera is perfectly fine. Okay, so that's telling you how to test the camera and acquire the data and how to present that. So here let's conduct comparison, okay, between the TOF camera, which is the red line here, and the purple line represents the still vision camera, and the blue line here represents the structured camera. Then let's see what's the strength and weakness. Okay, so as I said before, in the previous slide, from the equation, the math telling you the iToF camera should give you a linear distribution of the error along the distance, which you see that within 2 meters, okay, the iToF camera pretty linear on the left side. That means on the right side, on the percentage representation, that will give you a constant value within 2 meters. It's about 0.2%, which is very, very accurate. Okay. And for the other two techniques, for stereo vision and structured light one, it's supposed to grow like with z direction in power of 2, and which is the curve on here. You see that very clear. And on the right side, then it's supposed to give you a straight line, which is like this is pretty much a straight line distribution, but a little bit associating around that center line. Okay. So then from this comparison, what you can see is the TOF camera provides you the best accuracy across the technologies, and the stereo vision one gives you kind of intermediate one, and the structured light one gives you worse one in general. However, if you look at the close distance within 1 meter here, okay, the structured light camera actually can perform as good as the TOF camera. And remember that structured light camera usually is much, much cheaper than the TOF camera. So it's most economic like a solution for close range. If you want to reach high accuracy, structured light can bring you that. Okay, so that's one of the reasons why the Apple choose the structured light technology for their Face ID. Okay, because it's a close range, and you want a low price for that, then the structured light is the pick. Okay, so I think that concludes the part for the first chapter. We explain how to get the data for accuracy analysis and how to present data, and we did a comparison between 3 different technologies. So let's go to the second part of the presentation, where I show you how to do the analysis for the spatial precision metrics. Okay. So when we talk about spatial precision, it's a data comparison to its own mean value. Okay, when you talk about the accuracy, it's kind of talking about the data you measured and compared to the ground truth. When it's comparing to its own mean value, we are talking about the standard deviation here. Okay, so that's the most straightforward way. So then simply you take the same depth map you captured in the previous procedure, and then you take the ROI there and calculate what's the mean value of the SDD, okay, within that ROI, and then you plot it with the distance. Then you get a similar curve you observed in the previous slides, right? It's pretty much the shape is similar to what we observe in the precision side in RMSE with distance chart. However, you see, okay, the order change a little bit, right? In the previous slides, the best performance is from the iToF camera, which is red. The second best is the stereo vision one, and the worst is structured light. But here you see the order change. Okay, when you look at the precision aspect, actually TOF still give you best. However, the structured light give you the second best, and the stereo vision one give you the relative like worst precision across different technologies. Okay. And also this trend is following the same prediction. Okay, the STD should have a second power polynomial growing here for those strict structure light and derivation curves, and the TOF camera give you linear at close range. So someone will maybe be interesting. Okay, what happened after 2 meters? Why it's no longer linear, becomes non-linear? Okay, usually when you use mass equation to predict the outcomes, that means you have an ideal condition, right? That means your laser from this TOF camera is infinitely strong and there's no influence from the environment, from the ambient light. However, the reality is at close range, this assumption is still true. Okay, you have strong laser and you have very minimum influence from the environment, ambient light. However, when the distance grows, when that exceeds the range of the laser, okay, the laser power becomes relatively weaker and the environment light getting stronger and stronger becomes the dominant factor, then your signal noise ratio start to drop significantly. And starting from there, then your accuracy for the TOF camera start, and the STD for the STD start to grow and your accuracy start to drop. However, even with that, you see still the TOF is best compared to the derivation and structure light. But still, that's the most expensive one also. Okay, so that's the most common way we look at spatial precision along the distance. However, this presentation representation format only show you one data point at each distance, right? You don't know the distribution. If you want to really have a detailed analysis, okay, on the distribution of the errors, in that case, you need to do a hot map. And how you do it is you take any depth map, you take the reading of each pixel, you subtract it to the ground truth, and you take the absolute value here. Because if you don't do that, there's a negative value there. It's harder to be handled by the color box. So it's easier just take an absolute value of that difference. Then this color will be representing you the error existing across the image. And this color bar here, the darker the color is, shows you less error you have. When it's black, that means your reading, depth reading is exactly the same as the ground truth. So the difference is zero. Okay. When you have something red, then that means you have huge error, some error like more than 20 millimeters at 1 meter. This testing is conducted at 1 meter. So if you compare those, you see pretty uniform distributed, and the error is very minimum. Like for TOF cameras within 1 millimeter, and the structure most time is within 1 millimeter. And the derivation a little bit higher, majority 1 millimeter something. There's something jumping up and down about 3 millimeter. But those are pretty good, and you see the error is random distributed. That means there's no significant systematic error here. Okay, so later I will show you some data which from the cameras who does have some problem in there. Then from this map you can see there's something wrong there. Here I'm just focusing on the procedure first. Okay, so if you want to quantify, okay, this will give you an idea how that's distributed. But if you really want to quantify that, you need to use a histogram to present it. Okay, so if you look at the histogram associated with each of those color map, okay, so the gray bars shows you how many pixels are within this range. For example, here is showing about 35% of the pixel is reading 1000 millimeter, which the ground truth is also 1000 millimeter, which means those pixels give you the exactly right readings. Okay, and of course, or you want the camera to be 100% accurate, then you want a 100% bar here. However, that's not realistic. Okay, realistically, you will get a normal distribution here on this gray bars. Okay, however, you want your gray bars to be more concentrated the better the camera is. Okay, the second thing we mark on this histogram is the red line and the green line. The red line indicates what's the mean value you are reading from the camera across the image, and the green line shows you what's the ground truth. And you want the difference between the green line and the red line to be as small as possible. That means the accuracy is presented here. You want that to be small, okay? And then the second thing, the precision is also presented as the range of this purple line, which is the 1 STD range. And you want your data to be more concentrated within this range, more numbers within this range, which is better. And from that, to judge that, you can see actually at 1 meter, this is tested off 1 meter. So the TOF camera give you the best, and the structure light give you second best, and the derivation give you kind of the worst one compared to the other two. Okay, which is agree with what you see on the curve also, right? But this one you can see the distribution. Okay, so as I said, the previous one, you don't see any big trouble there, and you do all see the good data. You do say, well, what should I find? And when something wrong, what should I see, right? So this slide shows you when something goes wrong, what you see. Okay, so the left side, all three cameras we compare here, they are stereo vision cameras, and the left side one is the Gemini 335. The mid one is the RealSense D415, and the right side is D435. And you compare the hall maps, they are at the same scale here. Okay. The hall maps, so this one, majority of the error, the noise is around 1 millimeter, some like 3 to 6 millimeters, but here you see a lot of them falls into 6 millimeters, and here you see something even grows to like a yellow, which is like 7 millimeters, and huge ones. And if you compare the histogram that having the same thing, the Gemini 335 give you the most concentrated data, and you gotta pick at about 20%. And use this one, you get a little bit noise on here, which will drop that by about 5% and more flat distributed. And this one, when you have the full frame, all have those spatial noise here and there, that's mainly due to the speckle pattern they have, the density is not enough. Then you get a very flat histogram here, which representing your data is not very stable and precise across the images. Okay, so that concludes the second part, like how do you evaluate your camera on the spatial precision aspect. The third chapter, which is the last section of this presentation, will be talking about, say, how do you measure and visualize your temporal precision metrics. Okay, when we talk about temporal precision, that means how stable your camera reading is along the time history. So in this test, so we want to test the data stability along the time, so we don't move the camera anymore. We just put the camera at a given distance. So for in this example, I put at 100 millimeters just because the size of the wall I have. Okay, so I put the camera 100 millimeter in front of the wall, and then we stay the camera stable there and capture for 10 minutes. Every second I capture one image, so in 10 minutes I will capture totally 600 depth images. And then I will use those 600 depth images to do my calculation and show how stable the data is. Okay, so then what you do, you have 600 images, and in each depth image, you have a selected ROI, and you can then go ahead to calculate what's the STD value and what's the RMSE value within that ROI. And then you can plot those values with the time history. So here from 0 second to the 600 second, which is 10 minutes. Then you're supposed to see a very flat line here, which will represent your camera is really stable. The reading is not jumping up and down, up and down. Okay, and of course you will see something. So here we keep all the reading range is 0.2. This is 0 to 0.2, right? This is 0.2 to 0.4, 0.1 to 0.3. So all the range is the same, so you can compare them. So it's 0 to 0.2 a range on the vertical axis. Then you can compare them. Actually, I would say it's pretty much similar here, right? And also the weakness for this representation is, so you only get one data point at each timing. You don't know the distribution, how that error is distributed. If you don't know the distribution, you don't know what's wrong with that when something goes wrong. So that's why also we need the hot map and the histogram help us to judge it. Okay, so here's what you do for the temporal precision processing. So you have 600 depth images. That means for each individual pixel on those depth maps, you have 600 readings in 10 minutes. Okay, so you take those 600 readings for each pixel, you can calculate what's the STD of those 600 readings. And then this calculated STD will representing how heavy, how big this pixel reading jumping is. Okay, and you show that as a color on this map, then you can see that. So here you see the iToF, the ToF camera, and the structure light camera give you almost the best. Okay, this one is almost, you can say 9% of the data even don't have any jump within 10 minutes. And most of the other point, if that jump, that's still around 1 millimeter. Okay, the data reading. But the structured light one is a little bit worse. Majority of the data is jumping between 1 millimeter and 2 millimeter within that 10 minutes recording. Okay, and you see some of the a little bit higher reading on here, but still pretty good. I guarantee you. Later you can see from the other comparisons. So the structured light here, okay, you can see, okay, 9% of the data is jumping around 1 millimeter up and down, and the other pixels are all jumping within 1 millimeter, which is pretty good. Okay, the second hot map we will be checking on here is called the RMSE hot map. So same thing, we have 600 images, and for each pixel, we have 600 readings. We can calculate what's the RMSE. The difference from RMSE to the standard deviation. In the standard deviation, you are subtracting that to your own mean value, right? So for RMSE, you are subtracting that to the ground truth. So that's why you can see a little bit more noise here, right? And or you can see the color is shifting a little bit from to the bright side, okay, because you are adding the spatial precision noise on this map also, okay. And here you might ask, say, oh, those pretty much similar, can mean same thing. What are you trying to look at those two, right? Why you need to do two tests so similar and try to measure something? So this slide actually will explain why we need to measure the STD and the RMSE map two times. Okay, very similar, but we need to measure both. Then comparing the difference between both those two hot maps, that can give you a lot of information, or more in-depth information. So for example, let's take the Gemini 335 example. This is what the IR dot pattern looks like. And you see a little bit of the similar distribution from here to here, right? Okay, so that means your pattern have a little bit in errors introduced by the pattern, because the ideal pattern is pure random and the density have to be very dense to give you ideal hot STD hot map. But here it's just a little bit, you see a little bit. And the spatial precision hot map usually tell you how heavy your lens system or imaging system is introducing the errors. And for Gemini 335 situation, you got a little bit error from the pattern, you get a just random noise from the lens system, and you adding them together. This is what the RMSE hot map is telling you. Okay. However, when that goes to D415, you see the STD hot map directly show you this heavy noise, just exactly the same distribution compared to their speckle pattern, because the speckle pattern, there's a randomity issue. It's just repeat pattern, or the pattern is the same, so there's no randomity between them. So then you got those errors, noise from the STD. And also that camera have some lens distortion issues, and you can see a distortion ring here, which bring all those errors. And in the end, when you look at the RMSE map, you see there's a significant difference from the STD hot map and the RMSE hot map, right? And basically it's introduced by the speckle error plus the imaging lens system error together, okay? And for D35, and you see more severe STD hot map noise from here, because the dot in density here is about half compared to the other two. So you get more severe noise here. And for the spatial one, so I think recently they changed their lens to a more expensive lens. So that ring is gone, and more it's like a random noise here. And you add them up, this is what is finally showing up on your RMSE. Okay, so by comparing your RMSE hot map and STD hot map, then you can know how much systematic error exists in my camera system, how much is from the pattern itself, how much is from the lens system, and how much it give me in the end. And if you look at those clean RMSE map and a little bit noisy and a very noisy one, in the end, that actually will be reflected on your actual rating. So this is a rating comparison. So you take the mean value within your ROI and calculate STD and RMS. You plot that with time, you see this with a very clean hot map, it's straight, stable. And this one, you see everything still within same range. Okay, 0.2, 0.4, 0.3, 0.5, 0.8, 1%. So it's all 0.2% in y-axis. Okay. But then you can see it's more severe vibration. We get more noisy hot maps. Okay, they are like giving you the same information. Okay, so to conclude, so different users, they may have different requirements and different needs to the different metrics of the camera in depth, accuracy, or precisions. So in general, SLAM users, 3D scanning users, AR, VR measurement application users, they care more about the accuracy, because their system accuracy rely on the depth accuracy from your cameras. And for the users like from AMR, from the service robots, for some other applications, they only just need to do the object detection, avoidance. So those they don't really care about the readings that much. They care more about the stability of data. That means the precision of the data. Okay, so that can help them reduce their misdetection rate, false detection rate, and also if the data is very stable, they can save some power on post-processing. Okay, and the second part is, so from this presentation, I showed you like Orbbec as one of the largest depth camera manufacturer. How do we test our camera? Okay, and hopefully this can help you to use this content as your guideline to do your own testing, to generate your own data. Then you can have your own judgment on which camera is better, which camera is worse. And more importantly here is we introduced a way here. Okay, we maximally use the visualized way to present the numbers instead of just giving you the numbers. On the market currently, most company only give you some numbers with those specs. It's really hard to understand and see the distribution. So here we present you like the easiest way to visualize those specs. And so this will help the engineers, designers, and also the decision makers to understand and interpret the data, and then eventually help you to make the right decision to make your product successful. Okay, so I think that concludes all the content today. So thank you for your attention, and any questions?
Thank you so much, Xin, for joining us to help viewers improve their ability to evaluate depth, accuracy, and precision metrics. To everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we hope you're enjoying the 4th annual Vision Spectra Conference. Thank you all so much for joining us.